just surfed the DeepSeek wave. Now it's time to dive into another exciting release. Kimi, like DeepSeek, it's open source and skips the complexity of Monte Carlo tree search, dense reward modeling, and value functions, sticking to streamlined reinforcement learning with auto-regressive prediction. But here's the twist. While DeepSeek starts cold with an AlphaZero style RL, Kimi opts for an AlphaGo master approach, warming up with supervised fine-tuning of chain-of-thought prompts before diving into RL. Plus, Kimi shines in multimodal benchmarks like Math Vista. Let's jump in.
You know how language models usually predict the next token in a sequence? That works well, but it relies heavily on large labeled datasets. Now imagine shifting that idea to reinforcement learning, where exploration and rewards expand the data dynamically. That's exactly what Kimi K1.5 does. This model is a multimodal large language model trained with reinforcement learning, and here's the kicker. It skips complex methods like Monte Carlo tree search and value functions. Instead, it focuses on simpler techniques like long context scaling and policy optimization. And guess what? It performs at a state-of-the-art level across multiple domains. One of the standout features is how it combines long chain of thought, long COT, and short chain of thought, short COT, reasoning. This allows the model to think deeply when needed, but stay efficient for simpler tasks. The results? Kimi K1.5 outperforms models like GPT-4 and Claude Sonnet 3.5 on benchmarks like AIME, Math 500, and Live Code Bench, sometimes by as much as 550%. Take a look at Figure 1. It shows how Kimi K1.5's long COT performance compares to other models in math, code, and vision tasks. In math, it scores 77.5 on AIME, leading the pack. In code tasks, it hits the 94th percentile on code forces and excels on Live Code Bench. For vision tasks like Math Vista, it scores 74.9, matching OpenAI's top models. This sets the stage for understanding how Kimi K1.5 simplifies reinforcement learning design while dominating reasoning tasks across multiple domains. Now let's dig into Kimi K1.5's introduction and its main components. The authors pose a challenge. Scaling language models based purely on more data and bigger architectures can hit a limit, because high-quality data is finite. Reinforcement learning addresses this by teaching models through exploration and rewards rather than static datasets. That idea is central to Kimi K1.5. Several innovations form the backbone of Kimi K1.5. The first is long context scaling, where the model's context window is extended to 128,000 tokens. To handle it efficiently, they reuse partial rollouts. This basically recycles parts of previously generated data to save both time and compute resources. The takeaway? Longer contexts directly lead to better performance. They also adopt an RL technique called online mirror descent. It's refined with sampling strategies and length penalties to stabilize results. They avoid complex approaches like Monte Carlo tree search, focusing instead on scaling the context length, which fosters enhanced planning, reflection, and correction. Additionally, the model is multimodal. Kimi K1.5 processes both text and visual data. A long-to-short method then transfers insights from long-chain reasoning to short-chain tasks. Check out Figure 2. You'll see that on benchmarks like Math 500 and Live Code Bench, Kimi K1.5's short-chain performance outstrips GPT-4 by up to 550%. It's all about scaling reinforcement learning and context length to achieve those remarkable gains. Let's move on to how Kimi K1.5 sets up its reinforcement learning pipeline. First, there's the crucial step of RL prompt set curation. You need prompts that cover diverse domains, like STEM and coding, span different levels of difficulty, and allow precise evaluation of the model's reasoning. The team uses automated filters and sorts prompts by discipline to keep things balanced. They also tackle reward hacking, where a model might guess an answer without genuine reasoning. To counter that, they avoid certain multiple-choice formats, and they carefully remove prompts that the model breezes through with no real thinking. The idea is to focus on questions that require genuine steps to solve. The next step is long COT, supervised fine-tuning. Here, the the model trains on a dataset of detailed reasoning paths, things like planning, reflection, and exploration. This helps Kimi K1.5 learn to generate more coherent, step-by-step logic. Put together, these stages build a solid foundation for Kimi K1.5's reinforcement learning methods. Now, how does Kimi K1.5 actually use reinforcement learning to strengthen chain of thought or COT reasoning? The process is all about breaking complex problems into a sequence of smaller steps. Each step is a thought moving closer to the final solution. Planning algorithms often construct search trees, trying different partial solutions. But here's a twist. Kimi K1.5 largely sidesteps explicit tree construction. Instead, it learns to approximate this process internally. Advances in handling long contexts mean the model can reflect on its own reasoning, identify errors, and self-correct without heavy computation at inference time. For evaluation, a reward model checks the final output. If it's correct, maybe it passes test cases in a coding challenge. Great. The model's parameters are updated to encourage that chain of reasoning. This approach aims for a balance between simplicity and powerful planning skills, letting Kimi K1.5 handle entirely new problems effectively. Let's delve into how policy optimization and reasoning length control come together in RL training. First, they use a method called online policy mirror descent. Picture it as a way to optimize for correct solutions while keeping the model from overfitting. They rely on a surrogate loss function to measure how likely the model's answers are correct and then update the model in small steps. They also encourage exploration. What if the model gets stuck between two reasoning paths? One correct, one incorrect. Instead of punishing the wrong choice immediately, the model is nudged to explore and possibly recover. This builds resilience in problem solving. Finally, there's the overthinking problem. Models can produce overly long reasoning chains that slow them down. To handle that, they introduce a length reward, nudging the model to be concise yet accurate. This speeds up training and makes the final reasoning more efficient. Here, the authors discuss a length reward system. The idea is that correct, shorter answers earn higher rewards than longer, incorrect ones. Early on, this can slow training a bit, so they recommend gradually increasing the penalty for long responses over time. Next, they cover sampling strategies to improve RL. One is curriculum sampling. Start with easier tasks, then move on to tougher ones. The second is prioritized sampling, which focuses on the toughest problems where the model struggles most. This way, the training resources go where they're needed. They also talk about generating test cases for coding problems, since many challenges don't come with built-in tests. The paper's approach pairs a test case generator with filters to ensure quality. For math problems, the focus is on different but equivalent forms of answers. They use a reward model inspired by Instruct-GPT to handle varied solution formats and keep the evaluation fair. All these steps create a more robust and efficient RL pipeline. Next, the authors look at two big improvements: better chain of thought reasoning and handling vision data. First, a new chain of thought reward model is introduced. By explicitly fine-tuning on examples that showcase each reasoning step, the model avoids guessing shortcuts and handles logical reasoning tasks more reliably. They mention it achieved over 98% accuracy in manual checks. Then, they move to vision data. Three categories are used: real-world images, like charts or diagrams, synthetic data, controlled settings for geometry, for instance, and text-rendered data, turning text into images for consistent processing. Finally, there's context compression to make long COT models faster. They mention techniques like model merging, combining a long COT model and a short COT model, and shortest rejection sampling, where the system picks the shortest correct answer. This keeps the model's reasoning detail while reducing the time it takes to generate answers. Here, you'll learn about the training details and the infrastructure that supports Kimi K1.5. Pre-training covers multiple domains: English, Chinese, coding, math, general knowledge, and even multimodal examples like captioning and OCR. This training rolls out in 3 phases: building fundamental language skills, integrating multimodal data, and then extending the context window so the model can handle really long sequences. Vanilla supervised fine-tuning comes next, where a carefully chosen dataset is constructed with a focus on reasoning tasks like coding and math. They have over 1 million examples, divided into general tasks and reasoning-specific tasks. The sequence lengths grow gradually, with multiple examples packed into each sequence to make training more efficient. A system diagram shows the entire reinforcement learning pipeline. Rollout workers generate data, a replay buffer stores it, and trainer workers update the policy. Feedback loops ensure the model gets refined iteratively. Overall, it's a structured approach that combines foundation datasets with advanced RL. The paper then introduces its large-scale reinforcement learning training system. Inspired by breakthroughs in complex game scenarios, they adapt RL techniques to boost reasoning in language models. The system works iteratively. A master coordinates rollout workers, which generate data, and trainer workers, which update the model. A replay buffer stores the data, while reward models offer performance checks. One notable innovation is partial rollouts for long context RL. Rather than running one super long response end-to-end, they break it into smaller chunks. This prevents any single trajectory from hogging resources. By storing partial responses, the system maximizes efficiency and can run tasks of different lengths in parallel. I also mention a hybrid deployment strategy that segments tasks, controlling quality by penalizing repetitive content. This aims to optimize resources and maintain strong generalization across various reasoning challenges. Here's more on that hybrid deployment approach, which splits training and inference seamlessly. They use Megatron for the heavy-duty training phase and VLLM for inference. A checkpoint engine coordinates everything. When training finishes, Megatron hands off its GPU resources and saves the model weights. Then VLLM picks up those weights for inference. During inference, VLLM replaces its placeholder weights with Megatron's trained weights. After that's done, the GPU resources can shift back to Megatron to train another batch. They use Kubernetes sidecar containers to keep the training and inference workloads close together, improving performance by allowing shared GPU usage. Dynamic scaling also helps. Idle GPUs can temporarily support inference without disturbing training. The checkpoint engine acts like a traffic director, managing the lifecycle of VLLM processes and quickly switching between training and inference. This cuts downtime to under a minute, making the system nimble and scalable. On this part, the paper covers memory management, code sandboxing, and how they evaluate the model. First, there's a discussion of how Megatron organizes and stores checkpoints to optimize GPU memory. They transfer checkpoints into a shared format that supports advanced parallelism. Next, we see a code sandbox, a secure environment where the model's code can run safely, and Canbox. It can switch container images for different programming languages or tasks, and uses a lightweight container runtimes. This makes it very scalable, starting more containers per second than Docker, for instance. Finally, the authors describe their evaluation framework, KIM. Kimi K1.5 is tested in text reasoning, code reasoning, and vision reasoning, using well-known datasets. This shows the model's versatility across tasks that require diverse skill sets. Now we come to the main results for the Kimi K1.5 long COT and short COT models. The long COT version excels at complex reasoning thanks to reinforcement learning and combined vision text training. On tasks like Math 500 and AI.me, it hits state-of-the-art results. Meanwhile, the short COT model uses supervised fine-tuning and distillation. It performs well on reasoning, vision, and text tasks, often outdoing leading models. Check out Table 2 and Table 3. You'll see comparisons of Kimi K1.5 to other high-profile models. Kimi K1.5 tends to shine, particularly in reasoning-heavy benchmarks. They also look at how performance scales over more training. The interesting finding: longer response lengths go hand in hand with better accuracy. This suggests that detailed chains of thought really do boost problem solving. Next, the paper tackles scalability and token efficiency in Kimi A1.5. It starts by examining how performance grows when the model's context length reaches 128,000 tokens. Look at Figure 5 here. You'll see consistent boosts in metrics like accuracy as the training steps progress. Having that extended context helps the model delve deeper into reasoning tasks across various fields. Then comes the long to short approach. Think of it as a way to transfer the benefits of long context training into a more compact, short context model. They compare different techniques like dynamic programming optimization, DPO, rejection sampling, and model merging. The results show how Kimi K1.5 short can reach high performance on benchmarks like MATH500, but still consume fewer tokens. Figure 7 illustrates these efficiency gains, highlighting how shorter models can still capture the reasoning strengths of their longer counterparts. Here, the authors investigate how scaling model size and context length influences performance, along with some ablation studies. Figure 6 shows that as token length goes up, scores improve on benchmarks like math and general reasoning. Longer contexts allow for deeper COT, which raises accuracy. Look at Figure 7 again. You'll see how the ENC 1.5 short models make use of rejection sampling and model merging for efficiency. They stay competitive in accuracy while using fewer tokens. On Math 500, for instance, these short models remain impressively strong. They also weigh scaling context length against just making a bigger model. Generally, larger models do better, but longer contexts can help smaller models catch up. So, context scaling might be a more resource-friendly route to better performance. They mention something about negative gradients too, hinting that this method further refines the RL framework. Now we turn to policy optimization and curriculum sampling. The paper highlights that picking the right optimization strategy is key to improving chain-of-thought quality without making training too resource-heavy. Their advanced optimization approach refines the best responses and doesn't penalize errors too harshly. Figure 8 shows it outperforms standard RL methods like Restreet, especially in complex tasks. Then, there's curriculum sampling. Figure 9 compares uniform sampling with a curriculum that starts easy and gets harder over time. This step-by-step approach helps the model build its reasoning muscles, so by the time it reaches challenging problems, it's much more capable. At the end, they mention how partial rollouts, curriculum learning, and optimized algorithms all make long-context reinforcement learning more scalable and efficient. Finally, we see more evidence of how these policy optimization techniques stack up against Restreet, this time in Figure 10. The new methods bring higher accuracy in tricky tasks like math and science. That's thanks to a fine-tuned approach that better rewards accurate reasoning. They also note that combining strategies like length penalties, curriculum sampling, and streamlined data handling allows for powerful long-context RL without using heavy-duty methods like Monte Carlo tree search. The result? A model that can tackle a wide variety of tasks while staying efficient. They wrap up with the idea of blending long-context training with short-context methods so you can get the best of both worlds: robust reasoning and lower token costs. It's a promising direction for building models that are both capable and efficient. And there you have it, Kimi K 1.5 in a nutshell. Thanks for joining me on this deep dive.